Deep-sea navigation depends entirely on sonar systems that can distinguish a rock formation from a submarine. These systems, along with life-saving medical ultrasounds, rely on a specific class of materials that we have used for decades without a clear map of their internal structure. These materials are known as Relaxor ferroelectrics. They are found in everything from high-sensitivity microphones to the actuators used in precision defense systems. Even though they have been integrated into global technology for over 50 years, the scientific community has lacked the tools to see how their atoms are actually arranged. Without direct observation, engineers were forced to design these systems using theoretical models. They were essentially working from a blueprint based on sophisticated guesswork rather than physical evidence. Relying on these unverified foundations creates a bottleneck. To build more powerful sensors or energy-efficient devices, we first have to confirm the physical reality of the materials themselves. For years, researchers used computer simulations to try and replicate how these materials store energy and react to electrical fields. These models operated on a specific assumption that the electrical charges inside the material were distributed in random, chaotic clusters. Because the models assumed these regions were disconnected, they often failed to predict how the material would actually behave when an external force was applied. This highlights the central problem in modern material science. As we use more AI and complex simulations to design new tech, the garbage in, garbage out principle applies. If the structural starting point is wrong, the final result will be inaccurate. Until scientists could verify the atomic arrangement at the nanoscale, development of next-generation sensors remained stalled. To move past these simulations, a research team from MIT and several collaborating institutions began a new investigation to find the material's true physical structure. They targeted a complex alloy called lead-magnesium niobate lead titanate, which is a standard component in high-performance defense actuators. To see into the alloy, they used a technique called multi-slice electron ptychography, or MEP. This method moves away from theoretical simulations and allows for the direct measurement of electron wave functions as they pass through the sample. By applying this technique, the team could finally provide physical data for the atomic positions that had remained speculative since the material's discovery. The process starts by firing a nanoscale beam of high-energy electrons directly at the material. As the electrons strike the atoms within the sample, they scatter, creating distinct diffraction patterns that act as a physical signature of the material's internal layout. The researchers scan the material sequentially, moving the electron beam across a strict grid and recording a new diffraction pattern at every single position. These scan points are designed to overlap. This creates a massive amount of redundant data, ensuring that every region is measured multiple times. An advanced algorithm then works backward to reconstruct the material's three-dimensional atomic structure. This technique replaces the guesswork of older models with a precise map of the material's architecture. The results of the MEP scan provided a very different picture than the random polarization theory many physicists had accepted for decades. The physical data revealed a highly organized, layered hierarchy of chemical and polar structures that spans from the individual atoms up to larger, visible features. These polarized regions are significantly smaller and much more closely correlated than any previous simulation had suggested. It turns out that specific chemical species within the alloy actively control the material's polarization based on the charge state of individual atoms. These findings show that the material's performance doesn't come from random interactions, but from a specific, multi-layered mechanical order that was previously invisible. These 3D structural maps are now being integrated into molecular dynamics calculations to improve their accuracy. By feeding real-world coordinates into AI-driven computational models, scientists can finally validate their theories against physical reality. This level of detail allows for the design of materials with specific electronic properties, leading to more efficient memory storage, even better sensors, and improved energy devices. We are no longer designing in the dark. With a physical map of the nanoscale, we can begin to engineer high-tech innovations with atomic precision.